Hello everyone! So today we are going to be talking about circles and angles, but problems 5 through 8 is mostly a series of proofs for a variety of formulas that we think that you guys should remember for math competitions. And so most of them are relating to how we find the angle of an inscribed angle or a central angle inside a circle. But before we go into all of that, there's a lot of terminology that you need to know for circles. Here is a circle set of all points that are equal distance from this point right here, and I'm gonna, from now on, I'm gonna label this point O. I don't think it's actually custom for people to name the middle point O, but I like to do it, so that's how it is. So a line that connects 2 points that are on the circumference of a circle, like this line or this line here, this is a chord. And so if the line goes through point O, or the middle of the circle, it's called a diameter. And this is the longest chord that you can have in a circle. But you guys don't actually have to memorize this. Just remember these lines are called secants. Then you also have lines that are called tangents. And that means that they only go through one point on the circle. So let's say you take this point here, draw a line through this, and this is a secant. And you can have more secants, like a secant right here, or a secant like this. But the important thing to remember is that they only go through one point on the circle, so they don't intersect on the other side. So these are secants. Oh, I should write down how you write chord, secant. Oh, sorry, tangent. Got them mixed up a bit. Sorry, all of these are tangents, so tangent. And then secants are lines that go through 2 points and cross outside of the circle. So a chord, they're just 2 points. Well, I suppose they're not really lines, they're more of line segments. Sorry, chords are more like line segments. And so secants would be more like actual lines, and lines continue on forever, while line segments don't continue on forever. So this is a secant right here, goes through 2 points on the circle. This would also be a secant right here, goes through 2 points on the circle. And this is basically our terminology for the lines that can go through a circle. And other than these lines, chords, tangents, and secants, we also have a few names for the angles that we can have in a circle. So this here, this angle right here, sorry, it doesn't actually go outside of the circle. This angle right here, over here, would be an inscribed angle. And in addition to the inscribed angle, if we take our center here, we can also have a central angle. And so the important thing to remember about central angles, so let's say that you have A and M right over here. The central angle, let's say this is 39 degrees. The central angle is also equal to the angle of the arc that it intercepts. So right here would be arc AM. And so the angle of arc AM would also be 39 degrees, because this is the central angle that intercepts it. So you guys should read the notes. I'm sure there's going to be more details about all of these terms, but I'm going to get into one of the proofs, and this is the longest one by far, problem 5, which is to prove that the measure of the angle formed by 2 chords with a common endpoint is equal to 1/2 the measure of the arc that it intercepts. Right, so this problem 5 is kind of hard to visualize, especially if you only have the words. So I've kind of drawn out the 3 scenarios where this formula is applicable. What we're basically saying here is that we have an inscribed angle here, and that inscribed angle for all 3 of these diagrams we're calling theta. So this symbol represents theta, right? And we're trying to say that theta is equal to 1/2 the measure of the arc that it intercepts. Well, the arc that it intercepts is AC. And the thing about arcs is that the measure of arc AC is equal to the measure of the central angle that also intercepts it. So in this case, the central angle that also intercepts it is called psi. And so we're saying that arc AC is also equal to psi. And that basically means that theta is equal to 1/2 psi. And so this is what we want to prove down here. Except I'm going to be kind of rewriting it because it's easier to prove this way. I mean, it's just an extra step, but theta, 2 theta, is equal to psi. I mean, these two statements are equivalent, right? And we actually have 3 scenarios where this formula is inapplicable, and we have to show that it is true, that this is true for all 3 of these scenarios, or else our proof isn't complete. Our first scenario is where our inscribed angle, theta here, also goes through the diameter of the circle. So it looks kind of like this. You have the central angle here, goes through one of the radii, but you also have this angle right here. So this is what this looks like. We also have another scenario where these 2 lines are both behind theta right here. So the inscribed angle is kind of like covering the central angle like this. And we also have further diagram where these 2 lines intercept. And so the reason why we have to actually prove it for all 3 of these diagrams is because the proof for all 3 of these diagrams is different. So what we prove here is not applicable to what we do here. Although, you know, all 3 of these proofs are very connected with each other. So the reason why I have it in this order is because we're going to prove this first, then we're going to prove this second, and then we're going to prove this third, because what we prove here is applicable to how we are going to prove this is true, and we're going to use the information that we gained from proving that this is true onto problem 3 over here. So in truth, problem 5 is the longest proof. I promise that, you know, problems 6, 7, 8 are both shorter because we have 3 parts to it, basically. Anyways, I've talked long enough. Let's get into the actual proof with problem 1 here. Alright, so the important thing to realize for problem 1 here is that radii are, all these radii, so this and this, these are congruent lines, and this is a congruent line too. So, and that is because all the radii from the central point O all the way into the circumference of the circle, all of these are the same length, because all the radius in a circle are the same length. So because we mark these 2, we can also say that these are that these base angles here are congruent, right? So because this angle here is theta, that means that this angle here, I'll write this in green actually, it might be more clear. We also say that this angle right here is also equal to theta, because in an isosceles triangle, when you have these 2 legs, when you have these two lines that are the same, that also means that these 2 leg angles are also congruent. So we can say that this is equal to theta, and if you kind of like draw an imaginary box right here, like this, you also say that these 2 angles are congruent, although that's not applicable right now. Right, so we know that these 2 angles are equal to theta. So now we're trying to figure out what this angle is. And the important thing to realize here is that this angle, which I'll call like M and psi are supplementary angles, which means that M plus psi is equal to 180 degrees, because this is a straight line. So we can rewrite M in terms of psi, and we can say that M is equal to 180 minus psi. So now you have 2 important kind of equations that you can write out in order to solve, you know, systems of equation. So we know that this right here is a triangle, and we know that all the angles of a triangle add up to 180 degrees. So 2 theta plus 180 minus psi is equal to 180 degrees. And so you can kind of simplify this problem. 2 psi plus 180, 2 theta plus 180 minus psi is equal to 180. If we subtract 180 from both sides, we get that 2 theta minus psi is equal to 0, or 2 theta is equal to psi. So we've proved that in this kind of scenario, psi is always equal to 2 theta and 2 theta is always equal to psi, which is what we wanted to prove here. So this first one was relatively simple. The important thing to realize is the radii are all congruent lines if it stems out from the center, or O. And when you have these two radii that forms an isosceles triangle, you can mark that the angles are also congruent, so 2 theta. And you can also use supplementary angles to figure out what this angle is. And so you can like rewrite this equation that says 2 theta plus 180 minus psi is equal to 180. You can simplify this down all the way into this. And this is important to realize, and you guys should like keep in mind this general format we have here, because it's important for doing problem 2. In problem 2, we're going to mark the radii again. So we have these two lines that are congruent, and what we're actually going to do is that we're going to draw a line we're going to draw a diameter actually, or a chord. We're going to draw a diameter through from B through theta all the way into the other side. So we kind of like split these two angles, split psi and theta in half. So instead of using psi, I'm going to rename these two angles right here. Rename this one psi 1, and we'll rename this angle, and I'm going to rename this angle right here psi 2. Then I'm going to rename this angle right here theta 1, and this angle right here theta 2. And if you kind of ignore this side, just focus on psi 1 and theta 1, you'll notice that this is the same exact format that we have up here, right? So you have, if you just like try to make this a solid line, if you kind of ignore this part right here, I'm not sure how well I'm covering this, ignore this part right here, you can see that we can apply what we learned over here, the formula we established over here, onto over here. We know that 2 theta 1 is equal to psi 1. And the same, we can do this for here. We know that 2 theta 2 is equal to psi 2. So let's write this down over here. 2 theta 1 is equal to psi 1, and 2 theta 2 is equal to psi 2. And so if we add up these two equations together, and we can do that, we get that 2 theta 1 plus 2 theta 2 is equal to psi 1 plus psi 2. And then psi 1 plus psi 2, well, we just split up the original psi, right? We just split this up into psi 1 and psi 2. But you can just add it back together, and you get that 2 times theta is equal to psi. Make sure you understand how you can like visualize this and realize that you can apply what we learned here onto what we learned onto establishing these two equations over here. All right, so that's problem 2. Problem 3, it's a lot trickier looking than the rest, but we can still use the same kind of trick that we did to do the proof for number 2, and we can draw another diameter. Except this time we're going to draw a diameter through C and O. All right, so this is a diameter we have drawn. I'm going to replace, I'll leave theta here and psi here, but I'm going to call this theta 1 and psi 1. All right, well, using what we learned here, you'll realize that we can apply what we learned here into what we learned here. And you'll have to kind of, I suppose you'll have to work harder to try to visualize this. But, all right, so right over here, you have this line going through right over here. And so you have this angle right here. And then you also have this angle right here, which is looking kind of like what we have here. I'm not sure if I can color code this even further. I'll try to use black. So you have this right here, and you have this right here. Theta 1 and psi 1, and they both intersect the same arc, and it's the same format as what we have here. So we can say that 2 theta 1 is equal to psi 1. And in addition to that, we can also draw out, I'll use green this time. We can draw out this angle and this angle right here. And you'll notice that they both intersect the same arc. So we can also say that 2 times theta plus theta 1 is equal to psi plus psi 1. And we're basically using what we learned in problem 1, right? So this is kind of the same format. I know it's a little bit difficult to visualize, especially with so many conflicting lines, but it is what it is. We have the black lines here, green lines over here. They make the same shape as this. And with these two equations that we have, now, we can subtract 2 theta 1 and psi 1 from both of these sides in order to get that 2 theta is equal to psi. And so we have successfully proven that the measure of the inscribed angle is equal to 1/2 of the measure of the arc that it intercepts. You don't actually have to draw the central angle every time, by the way. So if you just see something like this, whoosh, doesn't matter where it is, or if it's like this, or if it's like, if it goes through diameter, doesn't matter what it looks like. You always know that the measure of this arc is equal to 1/2 the measure of this inscribed angle is equal to 1/2 the measure of the arc that it intercepts. So AC arc, this is equal to 1/2 AC. And this is applicable for all angles that are inscribed inside a circle. Right, so I've drawn the diagram out again. Problem 6. I'll read it aloud again, but it's kind of easier to understand it just by this diagram. Proof that the measure of the angle formed by two secants, so these two secants here, I'm going to label them actually, A, B, and C. These two secants, AB and CB, we're going to prove that the measure of this angle, so theta, formed by these two secants, which intersect outside the circle, so intersect here, outside the circle. It's not inscribed angle, by the way. Theta is not an inscribed angle. We're going to try to prove that this is equal to 1/2 the difference of the arcs intercepted by the secants. So the arcs intercepted by the secants in this case is arc A and arc B. I should say that it's the absolute difference of the secants intercepted by these the absolute difference of the arcs intercepted by these two secants. So we're trying to prove that theta is equal to A minus B divided by 2. And we're going to do that using what we learned previously from the inscribed angles theorem. So first, and this is kind of important, you'll realize that when you're doing these kind of proofs, sometimes you just have to add an extra line to make your life easier. And I'm going to draw this line right here. So what do we know from this? Well, this here inscribes, this is an inscribed angle, and it intercepts this arc, arc B. So that means that this inscribed angle, the value of it, the measure of it, is equal to B divided by 2, or beta divided by 2, I believe that's what it's called. And this arc over here, it intercepts, this angle over here, this inscribed angle over here, it intercepts arc A. So that means that it's equal to arc A divided by 2. And I feel like I should note that maybe these might be alpha and beta, but I'll just call them A and B. And we're trying to figure out theta, but because we know that this arc over here is equal to A divided by 2, and these two lines are supplementary angles, we can figure out what this angle is equal to. It's equal to 180 minus A divided by 2. And we basically have all the components we need at this point. You might notice that this here, and I'll draw this in green too, this over here is one big triangle. So we know that all the angles in a triangle add up to 180 degrees. So we can say that 180 is equal to 180 minus a over divided by 2, this is one of the angles, plus beta divided by 2, b divided by 2, plus theta. Right, and now we can simplify this problem. 180 is equal to 180 minus a plus b divided by 2 plus theta. Subtract 180 from both sides. 0 is equal to negative a plus b divided by 2 plus theta. And then we're going to subtract negative a plus b divided by 2. We're going to subtract this from the side, and we get that theta is equal to a minus b. And I was drawing the fancy b before, but it seems like I've given up on that. Theta is equal to a minus b divided by 2. And I'm pretty sure that this represents alpha and this represents beta. But I guess we're not going to use too formal language. And for proofs like this, you don't actually have to write too much justification. I always say, like, add a few lines explaining what you're doing. And this is a pretty self-contained proof. Theta is equal to a plus b minus 2, and these are values of a plus b. Okay, this was a relatively short proof compared to problem 5, so I feel comfortable enough to power through. On to problem 7, 2. Prove that the measure of the angle formed by a tangent in a chord is equal to 1/2 the arc that it cuts off. Again, this is kind of confusing terminology, and it makes a lot more sense if I actually draw out the diagram. So I have here and for the problem I have formed by a tangent and a chord. So here we have a tangent and it meets at only one point, and then we have a chord. So let's say this chord looks like this. I'm going to label this A and this B, and we're going to call this tangent M. And we want to prove that the measure of the angle formed by these two, so this angle right here, is equal to 1/2 the arc that cuts off. So 1/2 of arc AB, and we're going to call this theta, is equal to theta. Theta is equal to 1/2 the arc of AB. And then we're going to call a random point on this. We're going to call this point C2, actually. Alright, so what we want to prove here, theta is equal to 1/2 arc AB. And what we're going to do again for this proof is draw another helpful line. And so I draw the center here, O. I'm going to draw a diameter from A through O, so it looks like this. Then this is 90 degrees. So what kind of information can we get out of this? Well, first of all, starting, we can see that this angle right here, so angle BAC or angle theta, or actually I'm going to start from somewhere else. We're going to start with, I'm going to need to label this point too. I'm going to label this point D. So we know that arc AB plus arc BD is equal to 180 degrees. And the reason why we know this, well, this angle, the central angle that intercepts this entire thing is equal to 180 degrees. So arc AB plus arc BD is equal to 180 degrees. And so we can rewrite this so that arc AB is equal to 100 minus arc BD. Like so. And so another thing that we can kind of glean from this problem, is the angles right over here. We also know that theta plus this angle right here, so this is angle BAC, angle BAD plus angle BAD, bad, is equal to 90 degrees. Because this is supplementary, this is 90 degrees, so this also must be 90 degrees. And another thing that we can figure out from this problem here is that angle BAD is equal to 1/2 of BD, right? Angle BAD is equal to 1/2 of arc BD, right over here. AB, sorry, not, okay, kind of miswrote this. It's equal to 180 minus BD. Arc AB plus arc BD is equal to 180 degrees. Right, so now we have these three equations. We can do a few helpful substitutions with what we have. So starting with this, well, we can substitute this in for here. So theta plus 1/2 arc BD is equal to 90 degrees. And then here we kind of define what AB is equal to. But instead of this, we can actually define this, and we can actually rewrite this in terms of BD again. Or perhaps not a great idea. Well, usually with this kind of like this mess of equations, the system of equations, sometimes you need to wrangle something out of it. 180 minus AB. So you can substitute this in down here. Whoosh. You get theta plus 1/2 of BD, which is 180 minus arc AB, and that's equal to 90 degrees. So theta plus 90 degrees minus AB divided by 2 is equal to 90 degrees. So subtract 90 degrees from both sides. Theta is equal to arc AB divided by 2. So the most important thing to realize about this is the relationship between the arcs and intercepted angles. Because you just to reconcile like the two worlds, to reconcile what we have here, you need to reconcile the measure of the arc and the measure of the inscribed angle. So you have BAD here. And once you realize that BAD, once you realize that these two angles here add up to 90 degrees, and this entire arc here adds up to 180 degrees, and once you reconcile BAD with arc BD, that means that AB must also be corresponding with theta. Theta is equal to 1/2 AB, angle BAD is equal to 1/2 BD, and so forth, right? And all of this theta and BAD adds up to 90 degrees, and 1/2 AB and 1/2 BD adds up to 180 degrees. Okay. Sorry. I wish I could have a more elegant solution. It looks kind of messy right now, and I shouldn't have used red, but this is the proof. This is problem 7. Hello. So, like most problems, problem 8 is better drawn than described. What we want to prove here is that, actually, I should read out the problem. What we want to prove is that the angle formed by two chords, so in this case, chord AB and chord CD, the angle formed by these two chords is 1/2 the sum of the intercepted arcs. So in this case, we want to prove that angle theta here is equal to the sum of the intercepted arcs A and B. So this is the equation that we want to prove. You'll notice that it doesn't really matter which way we chose, because these two angles here are vertical angles. So if this is equal to theta, this is also equal to theta, and this part is equal to 100 minus theta. And the trick to this proof, like the previous proofs that we've done before, is adding a clever line. So we're gonna add a line like so. We're gonna add chord DB, I guess. And what we can do with this line, so we can name some angles. Right, so let's look at this angle first. angle CDB. Well, angle CDB intercepts arc B, which means that it's equal to arc B divided by 2. That's from our inscribed angles theorem. And we can also figure out what this arc here is. ABD. ABD intercepts arc A, which means that it's the measure of this arc over here. This inscribed angle is sorry, I keep on using the terminology incorrectly. So the measure of this angle, this inscribed angle right here, ABD, is equal to 1/2 the value of arc A. So that's A divided by 2. And so now that we kind of have this set up, well, using what we did in our previous lecture, where we have to remember that all the angles, the sum of all the angles in a triangle add up to 180 degrees. So now that we have this over here, 180 plus theta plus b over 2 plus a over 2 is equal to 180 degrees. So now we can subtract 180 from both sides. Theta plus a plus b divided by 2 is equal to 0. Oh, sorry, 180 minus theta. I was wondering what was going on. Minus theta, so this is negative theta. We add theta to the other side, and then theta is equal to a plus b divided by 2. And the important thing to know about this problem is that you can't underestimate how clever it is to add this line right here. Because we added this line right here, we can determine the value of these two angles over here. We've also formed a triangle, and those components were vital to our proof over here. That's what we did for our other proofs as well. I would say that when you're doing problems like this, look to create inscribed angles or to try to figure out inscribed angles, especially with arcs. Because if you have the value of an arc but you don't have a central angle, like point O is not labeled, that means that this arc over here might only be helpful for determining the value of the inscribed angle that corresponds to it. And of course, drawing this line has another value, which is creating triangles, because if you have a triangle, you can figure out what the sum of all of that is, and you can figure out some helpful details about theta here. Also, supplementary angles, that's pretty important too. I should list out like stuff that were pretty important for the proofs that we did before. First was what we learned today, inscribed angle theorem. And the other one was the sum of angles in a triangle, which is 180 degrees. Third one is supplementary angles, which add up to 180 degrees as well. And we basically used these three tools, and we were able to figure out, a variety of proofs. Anyways, I will leave the video here. I would say that some of these proofs have different solutions. I try to choose the ones that were most simple, but there's a few more complicated ones that are more self-contained for problem 5 especially. Anyway, guys, thank you guys for watching. Any questions, feel free to email us. Good luck on your homework sets.